Welcome to this video. My name is Pranav. I'll walk you through how I built an autonomous mobile robot that navigates a landmark-free 10 by 10 square foot arena, picks up 9 colored blocks in the strict red, green, blue sequence, and delivers them to a construction zone. I'll cover the hardware, controls, perception, and planning. So let's get started. My robot platform is a DF Robot Baron differential drive robot, powered by 4 DC motors controlled by an L298H bridge. The main processor is a Raspberry Pi Model 4B, and I've equipped it with a Pi Camera 2 module for vision, an ultrasonic sensor for collision avoidance and relocalization, an IMU and magnetic encoders for motion control, and a servo motor-based gripper for picking up the blocks. The robot uses a closed-loop proportional controller for motion. The magnetic encoders continuously update the robot's X and Y position during the straight-line movement. The IMU provides heading feedback during in-place turns. By comparing the commanded pose to the measured pose, I compute proportional corrections to the control input. This simple strategy keeps the robot on track with just a few centimeters of error, although odometry drift does build up over longer runs. The video feed from the Pi Camera 2 is pre-processed by masking out the top 25% and the bottom 25% of each frame. This helps reduce false detections from ambient light or background clutter. And then I segment the colors in the HSV space to detect red, green, and blue blocks and detect contours, filter them by area and shape based on the known geometry of the blocks. For valid detections, I estimate the distance of the block using its apparent size in pixels and the horizontal angle offset relative to the camera's optical center. To ensure accuracy, I also understart each detection using pre-calibrated camera parameters, and then I'd convert the detection from the camera frame to the arena frame using the robot's current pose so that I can place it accurately on the map. For path planning, I quantize the map into a 240 by 240 occupancy grid and connect each cell to its 8 nearest neighbors, and provided the straight line path is clear of obstacles. And then I run an A-star search on this graph to find an efficient path to the target block or to the drop-off zone. And after A-star search, I perform a line of sight smoothing step that removes unnecessary waypoints, resulting in a smooth collision-free trajectory. On the Raspberry Pi, planning and smoothing together take less than a second. One major challenge that I identified very recently was my helper script I was using to fetch the IMU heading. This script would create a new IMU object whenever it was called. My modular code base included multiple smaller scripts that needed access to the IMU heading, and that meant multiple IMU instances were being created unintentionally whenever I imported the IMU module, and that led to data races and inconsistencies, and sometimes even total data loss. So to solve this, I built an IMU server that runs on a dedicated UDP port, and the IMU is initialized once. It acts as a server, continuously broadcasting the latest heading data to the port, and any client script can now subscribe to this data without instantiating a new object. And I used a similar client server architecture for the Sonar server as well, Sonar sensor as well. And of course, that was on a different port. And this made the system much more reliable and stable. Another tricky issue I faced was with block distance estimation. When a block is not perfectly parallel to the camera plane, for example, if it is at an angle, it appears wider than it actually is. So my system originally used the apparent width of the bounding box to estimate the distance, so these rotated blocks would be detected closer than they actually are. So to fix this, I applied some basic trigonometry. We know the actual block has a fixed width, but if it is rotated by an angle, say theta, the it appears wider by a factor of 1 over cos theta. So if I estimate the angle of rotation using the shape or aspect ratio of the bounding box, I can adjust the apparent width to compute a more accurate distance. In test runs on a makeshift arena scaled down to 7.5 feet by 7.5 feet area, the robot completed the full sequence reliably with placement errors under 5 centimeters on average. During the final challenge, unfortunately, my robot was disqualified early in the run, but here's what happened. I placed the robot too close to the wall in the landing zone. As it completed its initial motion towards the opposite end, the in-place rotation before kicking off the search rear-ended the wall, which led to the disqualification. It was an oversight on my part and a valuable lesson in the importance of initialization and startup checks. For future plans, I plan to implement a startup safety check to verify clearance before rotation and add recovery behaviors in case the initial heading is compromised. Even though my robot didn't complete the challenge on the big day, I don't consider this a failure. It was an excellent learning experience, both technically and in terms of project experience. Huge thanks to Dr. Mitchell, who was always there guiding us throughout this course. His commitment, to making this course happen is always an inspiration to all students. Thanks for watching. If you have any questions or feedback, please feel free to leave a comment down below. And if you found my project interesting, please consider subscribing to my channel for more robotics content.